Okay, so now we're on 7 through 10 on our Unit 9 review. Number 7 says, with pressure, volume, and temperature being known values, the ideal gas law can be used to calculate blank. Okay, so all you have to do is look up on your formula chart the ideal gas law if you can't remember it. The ideal gas law is, remember, is PV-NRT, PV equals nRT. Okay, and what does it stand for? P stands for pressure, V stands for volume, N stands for the number of moles, R is your gas constant, and T is temperature. So it says if you know pressure, volume, and temperature, what can you calculate? Well, R is the constant, so you don't calculate that, that's known. The only thing that is left is N. So you can calculate the number of moles of your gas particles. All right, number 8. If temperature of a gas changes, but the number of moles and volume remain constant, what value must also change? Okay, so if we're keeping our moles and our volume constant, there's only 4 things that you can mess around with in gases. You can mess around with pressure, volume, temperature, and the number of moles. So we're not messing with moles, we're not messing with volume, we're messing with temperature. Okay, so the only other thing that can change is pressure. And remember, temperature and pressure are directly related to each other, and that is Gay-Lussac's law. Okay. And remember, that's the one equation that is not on your formula chart. It's on the combined gas law formula chart, formula. But Gay-Lussac, remember, is initial pressure over initial temperature is equal to final pressure over final temperature. And they are directly related to one another. And you can see that in the combined gas law equation. P1 V1 over N1 T1 is equal to P2 V2, sorry, that's kind of an ugly 2, over N2 T2. All right, so if this is keeping our moles and our volume the same, moles and volume the same, the only thing that's left is pressure and temperature. Do you see that? All right, so on to number 9. Which of the following is not one of the postulates of the kinetic molecular theory for ideal gases? Well, I talked about this when I went over number 1 as far as what the kinetic molecular theory entails. All right, so remember, ideal gases are ones where the particles don't take up any space, okay, that they don't have any intermolecular attractive forces, meaning that they don't get attracted to each other. Or repelled by each other, and they're also not attracted or repelled by the container that they're in. And they're always in constant random motion, and they move in straight lines until they collide with something, and those collisions are perfectly elastic. Okay, this is straight from your notes that I gave you at the beginning of the gas law stuff. So let's see if we can find one that is not true. Okay, so the point is that it's not true. Particles are in constant random motion. Note, that is a postulate of the kinetic molecular theory. The particle size is very small compared to the space between the particles. Yes, that is true as well. They need to be very small. All right, particles attract and then repel each other. No. Remember, the postulate says that they do not attract or repel each other. And the collisions between the particles are elastic. Yes, that is true for the kinetic molecular theory. So remember, they do not want to attract or repel each other. That is an ideal gas. Okay? All right, so that's number 9. Number 10, a fixed quantity of gas is placed inside a container with a fixed volume at a temperature of 27 degrees Celsius. The gas has a pressure P. Which expression shows the pressure of a gas at 57 degrees Celsius? Okay, so obviously we've got temperatures changing here, okay, and we're talking about pressure. So this is Gay-Lussac's law. All right, so we know that Gay-Lussac is P1 over T1 is equal to P2 over T2. All right, and if we look, we don't actually have the pressure numbers. We do have temperatures, but remember your temperature values need to be changed into Kelvin. So our initial temperature is 27 degrees, but we need to add 273 to that, and that gives us 300 Kelvin. Our second temperature is 57 degrees Celsius, and we add 273 to that, and we get 330 Kelvin. Okay, so now if we start plugging some numbers into our equation here, we know that we've got the initial pressure, and that is over 300 Kelvin. And then our final pressure is over 330 Kelvin. Okay, so remember, whenever we have equations like this, we need to cross multiply. Okay, so that means that our initial pressure is multiplied by the 330 Kelvin, and that our final pressure is multiplied by 300 Kelvin. Okay, so now if we're trying to figure out what expression shows the pressure at that final temperature, that means that we're solving for P2, so that means we need to divide both sides by 300. Okay, so that cancels that out. So this is what we're left with right here. We're left with the pressure times 330 divided by 300. So our answer choice is A, 330 divided by 300 times the pressure.